Good morning to all of you. So, in this class, after completing the semiconductors, we are going to learn about magnetic materials. So, basically, we are looking at the phenomena of magnetism in solids. So, magnetism is in solids. That's the topic that we are going to discuss. So, origin of magnetism. It is in a very classical picture that you already know about. Is that if you have a wire and current is flowing through it, the induced magnetic field can be given by right hand thumb rule. So if this is the wire that we can talk about, then the direction of magnetic field would be as shown in the, just you put your right handed thumb pointing in the direction of current, then magnetic field will be then curl your fingers, that is the direction of magnetic field. So similar to this, we now know that electrons have spin, they also have orbital motion. So these are the things that can contribute to magnetism, give rise to magnetic moment individually on an atom, and that's what. Uh, so that is the origin of magnetism. So electrons. So it is the magnetism originates from electron spin and electrons orbital motion. So, and we have also learned in the past few classes in term symbols. So while discussing term symbols, I told you how the coupling between spin and orbital magnetic moment occurs in different type of materials. So overall, this magnetic moment is given by the combination of spin and orbital magnetic moments. But most of the time, in many complexes, also you must have learned earlier, yeah, that it is sometimes it is only the spin that contributes, that is the major contribution. Orbital magnetic moments, several times it is quenched, or it becomes zero for some reason. So so what we are mainly concerned with finally is the spin, that so precession of electrons about their own axis gives rise to this kind of spin magnetic moment. We know that. And orbital magnetic moment also we already understand why it is, so how it is, it arises. So you have electron spin magnetic moment, due to the spin, magnetic moment due to the spin, and magnetic moment due to the orbital motion. So both of these things, you can, so yeah, this is the nucleus, and this is the electron that is moving around. So this is the orbital motion. This is the spin. So due to spin, there is magnetic moment. There is also a magnetic moment due to orbital motion, and both of these can contribute. And in many cases, it is only the spin that contributes most of the time. So this is the picture that we have seen earlier. So observed magnetic properties is due to the spin and orbital magnetic moments. Okay, and how the coupling between L and S, the two angular momenta, happens, that is shown schematically shown over here. So I told you that this is the angular momentum, so these are the angular momentum, due to this is the orbital angular momentum, and this is also angular momentum. This is due to spin, and then each one of them, each one of these can give rise to magnetic moment. So we are treating the electron as a tiny magnet. So electrons behaves as each of these electron. So this electron behaves as tiny magnet. This is the electron, and this behaves as a small, very small magnet. So, and the magnetic field is magnetic moment is directly proportional to the this L, the angular momentum of orbital angular momentum, or it is directly proportional to S, the spin angular momentum. So this is what we know till now. Spin angular momentum. Okay. So spin angular, so direct proportionality is there, and when you remove the proportionality constant, a term which is so when you have this thing, you have gamma E L. So this is the proportionality constant, gyromagnetic ratio, which is called gyromagnetic ratio. It is EH by ME. So that is the gyromagnetic ratio. In a similar way, you can also get the magnetic moment due to spin. But in this case, we have additional factor. In addition to the gyromagnetic ratio, the proportionality constant, we also have a number appearing in the two. So that is for the that is the G factor, because it takes into account the relativistic phenomena that can happen with the spin, G factor. So that is, so it was added to the formula later on when actual measurement of the magnetic moment gave rise to two things, like it was found to be twice that of the what was initially thought from a simple formula. So that was later on it was corrected, and this factor G factor was included in the formula to account for that relativistic effect in the due to in the spin. So we also know now how L and S can couple together, how can they interact, and we can get to overall angular momentum, that is overall angular momentum vector, total angular momentum vector, which is J, L plus S. So this is L, this is S, and J is L plus S. So here the two L and S are pointing in the same direction, and so uh, in in this particular case, L plus S is high in. So this when the electrons, so in case of electrons, as seen in the previous picture and even in this picture, what you are seeing as this green one, this is the magnetic moment. Uh, this is the magnetic moment, and it is pointing in the opposite direction to the angular momentum. Magnetic moment, or mu, what is mu? It is the moment of the magnetic dipole, or in short we say, simply say, magnetic moment. In short we say magnetic moment. Okay, so magnetic moment of electrons are pointing in the opposite direction to the angular momentum. Okay, and that's related to the gyromagnetic ratio, because the charge is different from this. So its gyromagnetic ratio is negative. and so the magnetic moment is always in opposite direction to the uh, angular momenta. So, and we also see that we can also note a difference that S, although small, the angular momentum due to spin is small, the corresponding magnetic moment is very large. Okay, and that is again, as explained, is the relativistic factor that comes into picture. Okay, so moment of the magnetic dipole. So every magnet that you can see or visualize is a dipole. It has north and south pole. So even if you take an electron, it is having both north pole and south pole. Okay, so that is how it turns out to be that electron. So that picture is important. If you have not forgotten that one, you shouldn't forget that one actually. Recently, just I had gave you we talked about that in that sense. Where is that? In the context of term symbols. In the context of term symbols, I had so all these things are interrelated. So you don't have to forget one thing. So yes, so don't forget this. This is an important picture when we talk about magnetism. This is the very important picture when we talk about electrons behavior, electrons behaving as small magnets. This is the thing. Sorry, small magnets, electrons behaving as small magnets. So this is so you have this field, a magnet placed on the right hand side, and in the same manner you are visualizing. See the color coding. This is north, this is south, and electron also has that north and south. So this is the dipole that we were talking about. Uh, an electron behaves as a magnetic dipole. So what I'm telling you that electron behaves as a magnetic dipole due to the spin. It is behaving as a magnetic dipole, and so when you and that is the origin of magnetic properties in a system. Okay, so there are no magnetic monopoles. You cannot have a separate north, separate south pole. Every material, every particle that gives rise to magnetic moment has both the north and south poles. Okay, and this is how you draw the magnetic lines of forces. It is important that you also learn the magnetic lines of forces. So it is drawn north to south outwards like this in a magnet. So and inside the magnet it will go like this. Okay. So inside the magnet it will be south to north. Outside the magnet that will be the magnetic field that you lines that you draw will be curving towards going from north to south. So it is so whenever you draw a magnetic uh, magnetic lines of forces, it is always like a snake biting its own tail. So a snake biting its own tail. So remember, this is how you draw the magnetic lines of forces for any magnet, even for an electron. You have to draw the same kind of thing. Okay. So electron, which is a magnetic, so in electrostatic sense, electron is a monopole. But when we look at the from magnetism point of view, we find that it is a magnetic dipole. And practically, it has not been possible to find any magnetic monopole. This point I already discussed in the offline class. So now we can move forward. So the interaction that I was talking about would be like this. When you have things happening, spin up or spin down electrons. So this this magnetic dipole is, when we say spin up, that means it is having north and south pole like this, arranged like this with a plus half, ms plus half. If ms is minus half, that is spin down situation, and this is what happens. The electric field in the direction of the dipole, magnetic dipole, is different. So that is how we see the electron as, and this is, it is so, as I told you, that all these magnetic properties are originate from electron. Okay, so with this background we can start learning about more about the magnetic materials. And where is this? Yeah, so this is the picture that we had. So that's what we saw, the magnetic moment due to spin and due to the orbital motion. So, and then the coupling of the two can give you different type of values. So if L and S both are pointing, both the angular momentum are pointing in the same direction, you get the high J, and this is the quantum number to describe the total. J is the quantum number to describe total angular momentum, and so it will also give you the total magnetic moment. Okay, in a similar fashion we can write the mu total will be proportional to uh, J. It will be given by J, quantum number J. So that also we had. So if the two angular momenta, orbital and the spin, is anti-parallel to each other, then that gives low energy state. If they are aligned, if both are pointing in the same direction, then that is the high energy situation. So now let's look at the periodic table and find, as I told you, that yeah, what kind of magnetism is observed in these in the entire periodic table. So this is the starting point of our uh, discussion on magnetic materials. So if you look at the periodic table, see the color coding has been done. Ferromagnetic is of this color, sky blue. Antiferromagnetic is purple. So now with this color coding, you can look at the periodic table and try to find how many of them are of what kind of magnetism is displayed, is observed in which kind of material. So when you talk of magnetic property, if you have a magnet that you see in life, in daily life, if you see a magnet and that attracts other pieces of iron or something like that, so those are ferromagnetic. That property is ferromagnetic, and you will see that there are only three ferromagnetic elements in the entire periodic table. Elements showing in the purest form, showing magnetism, ferromagnetism, there are only three: iron, cobalt, and nickel. So, sorry, iron, cobalt, and nickel are the three showing ferromagnetism. Okay, beyond that, you do not have, so no other element shows ferromagnetic properties. A very important point. Okay, this is an important point, many people may confuse. So this is the purest form of elements, and in the purest form only three show ferromagnetic properties. And in the same picture, if you see in the same series, DC 3D series, if you see chromium, it is the only element that shows antiferromagnetic property. And then you have rest of it, which you so we'll learn about these terms one by one and try to see. So our main focus will remain on the ferromagnetic materials, but because that is what goes into making of the device of ferromagnetic materials. And ferrimagnetism is not observed in pure elements. There is also another type of magnetism that is called ferrimagnetism, but this is not observed in pure elements. Observed in pure elements. So this was the point. So this we will talk about later. But these four types of magnetic properties, ferromagnetic, antiferromagnetic, paramagnetic and diamagnetic, can be found in the periodic table for the elements in the pure form. Ferrimagnetism will be found in oxides, mixed, usually in mixed oxides. Okay, it is observed in mixed oxides, and we'll talk about it later. So what you see here: iron, cobalt, nickel, ferromagnetic, chromium, antiferromagnetic in the entire periodic table. These are the distinguishing feature. The rest of it, the white shading that you see is the paramagnetic. So all to the left hand side, most of the elements, left hand side of the periodic table, you find most of the elements are paramagnetic, whereas on the right hand side, and including hydrogen, they are all diamagnetic. These are diamagnetic, most of them, exceptions being oxygen, aluminium, tin. Oxygen is paramagnetic, aluminium and tin are also, they also exhibit paramagnetic behavior. Okay, so yeah, so classification of magnetic materials, they can be classified according to their behavior. Diamagnetism, paramagnetism. So a diamagnetic, so when you put a material which a diamagnetic material is one which is having all the spins are paired, and when you put such a material in the magnetic field, then it is slightly repelled, very very slightly repulsion it will feel, and that is the it will move away from the magnet. In contrast, a paramagnetic material, when you put it in the magnetic field, it will feel attracted to the magnet, it will stick to the magnet. And this difference I had also shown you in the first semester by comparing liquid nitrogen with liquid oxygen. So that was one of the examples showing diamagnetism and paramagnetism. Uh, so paramagnetism, as we saw, is the property that is the uh, most of the elements in the periodic table, they are paramagnetic. Most of the elements are paramagnetic, and that is the most dominant feature of the periodic table in terms of magnetism. So but in practice, in practical life, you will have all these things: diamagnetic, paramagnetic, whatever they are, antiferromagnetic, these are all treated as non-magnetic things, because if you bring them towards a magnet, they won't feel attracted. Sorry, they do not retain the magnetism property, when there is no, in absence of any magnetic field. But there are certain materials which, even if the external magnetic field is removed, you can see that they attract two pieces. So a magnet, when brought in front of a iron, metallic iron, it shows attraction. So the magnet is actually the permanent magnet that you have is a ferromagnetic material. So it is the ferromagnetic material which are most important to us. And then next important material will be ferrimagnetic, which also retains magnetism, but that is not found in the pure elements, as I told you. Uh, Other types of diamagnetism or paramagnetism is the elements that show these properties are said to be non-magnetic, whereas only those which show behavior, ferromagnetic behavior, you call them magnetic. So जो फेरोमैग्नेटिक बिहेवियर शो करते हैं उन्हीं को आप मैग्नेटिक कहते हैं प्रैक्टिकल लाइफ में. इसके अलावा फेरी मैग्नेटिक भी आएगा, लेकिन एलिमेंट्स में प्योर फॉर्म में वो कभी होता नहीं है फेरी मैग्नेटिक बिहेवियर. Ferrimagnetism is only for oxide. So ferromagnetic and ferrimagnetic are the two things that defines, you say that the substance is magnetic. क्योंकि चुंबक से जो अट्रैक्टेड फील करेगा उसी को आप कहेंगे ना कि ये मैग्नेटिक बिहेवियर शो कर रहा है. डेली लाइफ में आप वैसे ही आइडेंटिफाई करते हैं. ठीक है, तो चुंबक से अगर अट्रैक्ट नहीं हुआ तो नॉन मैग्नेटिक है. तो यूजुअली अगर आपके पास डायमैग्नेटिक है या पैरामैग्नेटिक मटेरियल भी है, नॉर्मली ऐसा कुछ आपको दिखेगा नहीं कि ये मूव कर रहा है इधर. So let's move on. So antiferromagnetism is another property that can be seen. So yeah, already I told you about ferrimagnetic behavior, but not observing any pure element, only in mixed oxides. And this name ferrimagnetism arrives from, it is typically found in ferrites. What is ferrites? Ferrites is Fe3O4. So the name ferrimagnetism arises from ferrites, and typically, so what I am saying here is that, so what I just am talking about is that you have ferrites. Ferrimagnetism magnetism is a term that originates from ferrites. Originates from ferrites. Ferrites क्या होता है? So ferrites के बारे में आपने सुना होगा, तो ये होता है ए अगर आपके पास एक या डाइवेलेंट मेटल, यहाँ एक की जगह एक ये लिखते हैं, एक डाइवेलेंट मेटल है और ये FeO4 MFeO4. so divalent metal. Most common example of ferrites is magnetite, example. So जो प्रॉपर्टी फेराइट्स में पाई गई, एक स्पेशल टाइप ऑफ मैग्नेटिक प्रॉपर्टी था, उसका नाम दिया गया फेरीमैग्नेटिज्म. So the word ferrimagnetism originates from ferrites. Ferrites are definitely, this is like AbO4, you can see. So this is oxidation state 2, this is oxidation state 3, like this. And example of that is magnetite. Magnetite इसको कहते हैं Fe3O4. Or you can see this is actually combination of FeO and Fe2O3. So you have oxidation state 2, oxidation state 3, like this. So you can, or you can also write it in form of this Fe2 Fe4. So that's what the general formula would be, something like this. Ferrites having one metal in this state, sorry, divalent state, another metal in trivalent state, and O4. So this kind of, they are called ferrites, and mostly this B that we are talking about is iron. So that's why ferrite. So you can replace this Fe here. You can have, if iron, so this is the magnetite, and if you replace this Fe with another zinc 2, sorry, we call it, so this is again Zn FeO4, so we call it zinc ferrite. Zinc ferrite. Similarly, if you have cobalt in place of CuFeO4, we call it cobalt ferrite, like this. So all ferrites have this typical property, that is ferrimagnetism. So it was a class of compounds that showed a typical magnetic behavior, which was named as ferrimagnetism. We will learn about this more. So this is the summary. This picture, this slide summarizes all different kind of behaviors. So I need to, it is going beyond the screen. Oh, slide. So it is better that I make it smaller. Okay, so this is the summary of different types of behavior that you can find in across the elements and their compounds, whether in pure state or whether in combination of with some oxides, what kind of behavior they show. So these are diamagnetism, paramagnetism, ferromagnetism, antiferomagnetism, and ferrimagnetism. These are the 1, 2, 3, 4, 5 types of magnetic behavior. Okay, so the first one, diamagnetism, means that okay, so it is shown by inert gases, gold, copper, mercury in metals, and non-metallic elements like this boron, silicon, phosphorus, sulfur. Okay, and then NaCl or H2, N2, H2O, most organic compounds. So all of them show diamagnetic properties. So in this, what you find that each of these atoms, none of them, no magnetic moment is present. This sorry, they have no magnetic moment, and because of that, and so when you put them in, so what is, so this, okay, on the extreme right you see a graph that is M versus H. M versus H. H is the applied field, applied magnetic field, and what is M? M is the magnetization. M stands for magnetization, and whenever we discuss magnetic behavior, this M versus H graph, this M versus H plot is very important in describing the behavior, and by looking at the nature of these curves, by looking at the nature of these plots, you can say whether what type of material it is, whether it is diamagnetic, paramagnetic. Everything you can decide by looking at this graph, that is M versus H. M plot. So this is the what I was writing here, no sorry, magnetization. So this is magnetization. What is magnetization? In a crystal, if you have, so let me put it this way, what is magnetization? So you can understand it this way. So what I was showing there is the like M. So you have, in a crystal you may have, so in a crystal lattice you have atoms arranged in a different order, and each atoms can, if they have certain individual spins, each atom can uh, have if they have unpaired electron, they have a net individual spins at each of these atoms. Net magnetic moment is there. So each of these is giving mu. These are the magnetic moments. So then summation of this magnetic moment over a given volume is called of magnetic moments. All these magnetic moments that we see in a crystal, uh, moments in a given volume or mass, total mass, is, this is your magnetization. So total magnetization is usually M, denoted by M, and it is summation of all these mu summation of individual magnetic moment arising due to each of these electron. So n is equal to 1, 2. So summation of these magnetic moments mu and over a given volume, or summation of mu n over a given mass of the solid substance that we are talking about. So total mass, or so you sum up all these magnetic moments, individual magnetic moments at different, arising from different points, and then if you collect it together over, so sometimes it is given as per unit volume, per unit mass also it is reflected. So if you have volume known, then you can calculate, multiply by density, you can get mass. So it is expressed in either way. Most of the time it is per unit gram, per unit mass of the material. So this summation of individual magnetic moments is magnetization that I told you. So whatever, if they are aligned or not aligned, they might be pointing in other directions. So whatever it is comes out to be. So that is the magnetization, and this magnetization is plotted over versus. So what you curve that you are getting, that is reflection of that thing. So what happens in that, in a diamagnetic material, when you have, so I will define a few terms that will give you so there's also in that chart you see, So these are terms that you will find appearing in the case of so M versus H curve. When you show plot of that, so M on the y-axis and H, so this is the applied field that we show on this axis. So in a diamagnetic material, what happens is that so paramagnetism is first easy to understand, so that's what we can think of. So in a paramagnetic, as you increase the applied magnetic field, the magnetization goes on increasing. So the magnetization goes on increasing. So this is H, applied field, applied magnetic field, and this is if magnetic field is applied in a particular direction, so this is the net magnetization produced, this is the magnetization. So remember, this is the summation of magnetic moments by volume in a given volume. Current mass, so total mass by total mass of the sample. So in a given, so total summation of it, so that is M, capital M. So and the graph, this is a typical behavior of a paramagnetic material. So gradually, as the applied field increases, the magnetization, that is the individual magnetic moments also, so the summation of these magnetic moments goes on increasing. So that is a typical behavior of paramagnetic substance, where you will get M versus H as a straight line, and when you reverse the direction of the magnetic field, it will go like this. So the spin will be inverted in that case. So reversing the direction, so this is the minus H side, this is plus minus, so reverse, so it is indicative of the reversing of the direction. So this is a typical, and what this you see, this slope is dm by dh. What is this slope called? This slope is what we know as susceptibility. This is called susceptibility. That susceptible आप कहते हैं ना, susceptible to something, कोई जल्दी बीमार होता है, susceptible to diseases, susceptible to cold and cough, susceptible का मतलब होता है कितनी आसानी से आप किसी को एक यहाँ पे मैग्नेटिक फील्ड अप्लाई कर रहे हैं और कितनी आसानी से उसमें मैग्नेटाइजेशन डेवलप हो जा रहा है. So that is susceptibility. If it is so a high susceptibility, high slope, uh, greater is the slope, greater is the susceptibility, and dm by dh is your magnetic susceptibility. That's yeah, that's the point. So this susceptibility, so we call it magnetic susceptibility because add the term magnetic here, magnetic susceptibility. The slope of M versus H curve will give you susceptibility. So this is the behavior of a paramagnetic substance. In a diamagnetic substance, what happens is that in a diamagnetic substance, what will happen? Sorry, I will just rub it off. Minus H plus H I was showing. So in a diamagnetic substance, when you put like nitrogen, liquid nitrogen, when put in a magnetic field, what you find that you apply positive, you apply a force, apply the magnetic field, and it will show the magnetization direction of it will show us very small magnetization, linear increase, linearly. So this kind of curve will come. So it will show a very small change in the, so it will show a very small change, very small change. So this is a typical graph. So positive, you are applying a magnetic field in a positive direction, it will show a very small change in this, and when you are applying, so similarly you can extend this graph on the other side. So this is the behavior of diamagnetic magnetic substance. Diamagnetic substance. So in a diamagnetic substance, what the difference here is that you increase the H and magnetization is negative. A very small negative value of magnetization is achieved. So it is the, so when you take this slope, chi is actually dm by dh, which is negative. Negative in this case. In the paramagnetic case, the susceptibility was, this is the susceptibility, that is uh, for unit, for small change in the magnetism, how much magnetic field, if you change the magnetic field by a very small amount, what is the change in the magnetization. So if it is very large, so you have a high value of slope, high value of susceptibility. अप्लाइड फील्ड के कॉन्टेक्स्ट में आप इसको देखते हैं, और susceptibility, yeah. So susceptibility is negative for diamagnetic substances, and this is what is shown here. ये जो आप देख रहे हैं, look at this curve. The susceptibility M versus H curve is turning out to be negative. They have only shown the positive H axis, so it is, so a small, very small negative susceptibility is obtained. So that is the key point of a diamagnetic behavior. And in case of, so it is on the order of 10 to the power minus 6 to 10 to the power minus 5. So very small change. And that's why you don't actually see when you put a diamagnetic substance like nitrogen in the atmosphere, all this negative magnetization is so small that you don't see that it being repelled. What it means that it should be repelled in the magnetic field. When you put it on magnet, it should be repelled, but it is so small, the value is so small that you don't actually see it happening. You see that nothing has happened, but actually there is a small force, repulsive force, that a diamagnetic substance will feel when put in a magnetic field. Okay. Second, paramagnetism already defined. What is, this is the most common thing that you all know. So metals, diatomic gases, oxygen, nitric oxide, these are all paramagnetic transition metals, rare earth metals, so, and their oxides. So what is the difference? The difference is that, so see this picture. In this picture, in the previous case, because there was no individual moments, the diamagnetic case, so it was, nothing was drawn. But in this picture, you can see that arrows have been put, red color, in different directions, right? So they are pointing in different directions, giving no net magnetic moment, no net magnetization when the magnetic field is not present. Okay, so this is, so individual spins are randomly oriented. They have spin, each of these atoms have net spin, uh, but when you look at the, in a crystal or in a molecule, when they are put together, large number of molecules are there, you put them, there's random orientations of the spins. So, but when you apply the magnetic field H, you see a gradual enhancement in the magnetization produced. So what happens that the net magnetization that you see is due to the alignment of the spins. The spins get aligned in a particular direction, giving you a high value of this M, increasing value of M that you see. हाँ 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 माइनस है, हाँ प्लस है, प्लस 10⁻⁵ है। क्या माइनस साइन है ना? अब हम आपको बोले तो अभी तो बोर्ड पे बताए, पीछे पूरा स्लाइड पे बताए हैं नेगेटिव साइन। हाँ हाँ वही यहाँ पे दिखाया जा रहा है, उसी को हमने बड़ा करके आपको फिर उधर बताया था ड्रॉ करके। और इस केस में अप टू 10⁻³ तक जा रहा है। देखिए 10⁻⁵ से शुरू होकर 10⁻³ पे जा रहा है। सो इसका जो स्केल जब भी ड्रॉ करेंगे, ये जब दोनों को दिखाना होगा आपको, डायमैग्नेटिक और पैरामैग्नेटिक को, डायमैग्नेटिक छोटा सा लाइन ऐसे नीचे की ओर जाएगा, पैरामैग्नेटिक उससे उसका स्लोप थोड़ा ज्यादा दिखाएंगे जब भी ड्रॉ करेंगे तो। सो यही डिफरेंस है। तो वही मैं कह रहा हूँ कि जब आप डायमैग्नेटिक सब्सटेंस का इतना कम वो मैग्नेटाइजेशन होता है जो उल्टे डायरेक्शन में होगा, कि वो आपको रिपेल होता हुआ दिखेगा नहीं। एक्चुअली इट व्हाट इट मींस दैट नेगेटिव का मतलब हुआ कि इट इज रिपेल्ड बाय द मैग्नेट, और ये पॉजिटिव होने का मतलब हुआ कि इट इज अट्रैक्टेड बाय द मैग्नेट। तो ऑक्सीजन को जब आप याद कीजिए, जो पहले फर्स्ट सेमेस्टर में आपको दिखाया था ऑक्सीजन और नाइट्रोजन का, लिक्विड नाइट्रोजन का बिहेवियर, वो यही था। अभी फिर से आप वो वीडियो देखिएगा तो फिर वह यही बात वो दोनों बोलते हैं, एकदम वर्ड टू वर्ड करेक्ट बोलते हैं एक एक चीज, कि नाइट्रोजन ऑल्सो बिहेव्स इन अ सिमिलर वे, कि बट इट विल बी इन द ऑपोजिट डायरेक्शन। ऑपोजिट मतलब उसमें थोड़ा सा रिपेल होना चाहिए, बट इट इज सो स्मॉल दैट यू वी डोंट सी एक्चुअली गेटिंग रिपेल्ड। वो दिखता नहीं है, इतना कम वो होता है। Diamagnetic substance is actually repelled by a magnet, and that means repulsion means you are producing magnetization in a reverse direction, उल्टे डायरेक्शन में। जो मैग्नेटिक फील्ड का डायरेक्शन है उसके उल्टे डायरेक्शन में आपका मैग्नेटाइजेशन प्रोड्यूस हो रहा है। मतलब स्पिन्स आर अलाइनिंग इन अ डिफरेंट वे। इफ ओके, सो हियर व्हाट वी सी, सो ये बहुत बड़ा डिफरेंस है डायमैग्नेटिक एंड पैरामैग्नेटिक में। Susceptibility is high, much higher, and so the graph will be always have a larger slope as compared to thin. In case of ferromagnetic, you even so paramagnetic में है, जब तक आपने external magnetic field apply किया, spins get aligned and you have a increase in the magnetization. As soon as आप external magnetic field हटा देंगे, सारा स्पिन फिर से रैंडम हो जाएगा और कोई नेट मैग्नेटिक प्रॉपर्टी उसमें नहीं दिखाई देगी। लेकिन फेरोमैग्नेटिक मटेरियल में क्या होता है कि इवन इफ द एक्सटर्नल मैग्नेटिक फील्ड इज रिमूव्ड, some of the spins on the atoms are still aligned in a pointing in a certain direction. So there is, even in the absence of magnetic field, that will happen, and that is they are used in making of a permanent magnet. जो भी आप permanent magnet कहते हैं सब फेरोमैग्नेटिक होते, ज्यादातर फेरोमैग्नेटिक ही होते हैं, या फिर फेरीमैग्नेटिक। फेरो और फेरी ही मैक्सिमम आपको मैग्नेट बनाने में यूज होता है। फेरोमैग्नेटिक, सो आयरन, कोबाल्ट, निकल, these are the examples of rare earth between alloys of iron ferromagnetic elements. Okay, so in this case the susceptibility is much larger. देखिए स्लोप यहाँ पे बहुत ऊपर उठा के दिया गया है, the line. So susceptibility is much larger as compared to paramagnetic. The difference क्या क्या है? And atoms have parallel aligned magnetic moments. susceptibility is very large. The slope dm by dh, this is much larger, and you also see that it is getting saturated after some point. So पैरामैग्नेटिक में सैचुरेशन यहाँ पे नहीं आता, तो सैचुरेशन के लिए नॉर्मली बहुत ही हाई मैग्नेटिक फील्ड चाहिए जो कि यूजुअली अचीव नहीं कर सकते हैं, लेकिन फेरोमैग्नेटिक में बहुत तेजी से ऊपर राइज करता है और सैचुरेट कर जाता है. इट इज दैट इज आफ्टर पॉइंट, आफ्टर दिस पॉइंट there is no change in the magnetization. Beyond this point there is no change. So there is no change in the magnetization after certain value of applied magnetic field. Initially there is a very sharp rise in the magnetization. So this is a typical feature of magnetic M versus H curve in the ferromagnetic behavior, and in fact we will see later that in the reverse direction it will give you like a curve which is if I can go to this in a ferromagnetic picture, if I can draw more elaborate manner, then you will have M versus H for a ferromagnetic material will be H. So initially it will like go like this, change the color to distinguish between the two. Okay, so if I can draw बहुत तेजी से राइज करेगा और उसके बाद सैचुरेट करेगा, then so this is called saturation magnetization. So ये जो पॉइंट हुआ जहाँ पे सैचुरेट कर गया, दिस इज कॉल्ड saturation MS, that is saturation magnetization. कि अब इसमें फर्दर चेंज नहीं हो सकता, जितना स्पिन अलाइन होना था सब अलाइन हो चुका है, अब जितना भी मैग्नेटिक फील्ड लगाओ कुछ चेंज नहीं होगा. सो दैट इज saturation magnetization. So this is the maximum change, maximum value of magnetization that can be achieved on application of magnetic field, a very high magnetic field. So that is your saturation magnetization. और इसके बाद जब हम रिवर्स करते हैं डायरेक्शन, when the so this is the direction that you move initially, and then on reversal of this direction, अब आप इसको अगर रिवर्स करेंगे तो फेरोमैग्नेटिक मटेरियल में यूजुअली so when we move back, and then so it will be come out to be something like this. So we are reversing the direction of the magnetic field, and then when we bring it to zero, so what happens is that when we bring it to this point so this is the ferromagnetic behavior that I am describing through graph. So in a typical ferromagnetic substance this happens. So you reach, so वापस आप जब magnetic field zero हो गया, when the magnetic field is zero, H is equal to 0 at this point, you see still it has some magnetization, a large value of magnetization remains. So this is called MR, M with a subscript array MR से इसको डिनोट करते हैं, सॉरी R is the subscript here. So MS हुआ saturation magnetization, इसको कहते हैं Remanent magnetization. Magnetization. Remanent magnetization is the magnetization that remains even after removal of the field of applied field, applied magnetic field. अप्लाइड मैग्नेटिक फील्ड को आपने हटा दिया और उसके बाद भी ये कुछ एक it shows a very large value of magnetization, so that is called remanent magnetization. So this is the characteristic of a ferromagnetic material, that initially when you prepare a small ferromagnetic material, it may not have anything, uh, uh, it will have randomly oriented spins, but as soon as once it is put in a magnetic field, it will undergo this kind of change. It will have reach a saturation magnetization will be achieved at a certain value, and when you reverse the direction, when you decrease the magnetic field gradually and reach a zero value of magnetic field, even then there will be some magnetization left. So you will need to apply a much greater magnetic force, magnetic field, in the reverse direction, in the minus h direction, reverse direction, to get a zero field. So this is what we call as HC. This point where what happens? So this is called HC, coercive field. So we are moving like this. So उस coercive field कहते हैं, मतलब the value of magnetic field that must be applied in the reverse direction to make the magnetization zero. So this is the amount of magnetic field in the reverse direction that must be applied to make the total magnetization zero. Okay, m is 0, you can see it is on the axis. So here m is 0, and to make that m is equal to 0, you have to apply a magnetic field. जब आप जीरो मैग्नेटिक फील्ड कर रहे हैं, अप्लाइड मैग्नेटिक फील्ड, तब वो जीरो नहीं हो रहा है मैग्नेट एम का वैल्यू, वो एक आपको और ज़्यादा मैग्नेटिक फील्ड अप्लाई करना पड़ रहा है रिवर्स डायरेक्शन में, तब जाके वो जीरो हो रहा है. सो दिस इज कोर्सिव फील्ड. सो इट विल अगेन इट फॉलोज द पाथ लाइक दिस. एंड ये जो पाथ है, जो ओरिजिनल जो आपने देखा डॉटेड लाइन से जो हमने दिखाया दूसरे कलर में, इनिशियल वाला पॉइंट, ये कभी भी फिर आएगा नहीं. देन इट विल फॉलो व्हेन यू इंक्रीज द रिवर्स डायरेक्शन, पॉजिटिव डायरेक्शन में जाएंगे, तो ये वाला पाथ फॉलो करेगा. और इस तरह से अब आप जितनी बार उसको you keep changing the direction of magnetic field, positive and negative direction, हर बार ये वाला पाथ फॉलो करेगा जो रेड कलर में कलर में दिखाया है. ठीक है, ये जो ब्लैक कलर से जो दिखाया था वो वाला पाथ फिर दोबारा फॉलो नहीं होगा. It is only the very first time when you put a substance in the magnetic field of if it is ferromagnetic, then it will go like this and then achieve a saturation value, and on the reversing the direction again you have the same kind of profile repeating on the other side. So this kind of thing, so we say that it so see, it was the ms high saturation magnetization, and when the field is removed, it is still showing some value as very closer to the saturation magnetization. It retains the value, and so we say that it remembers its history. So what we call, so the substance is having remanence magnetic, it remembers its history That is what happened to it when you applied a very high value of magnetic field. It got aligned, it has very high value of magnetization was achieved, saturation magnetization, and almost very close to that, even if the field is removed, it is retaining these things. So this is the remembering its history. We call it hysteresis. This kind of profile is called magnetic hysteresis. Sorry, hysteresis. Hysteresis. So this is the hysteresis. This kind of loop, if you are getting MH loop, we call it magnetic hysteresis curve. And so a ferromagnetic typically shows this kind of hysteresis profile. So which is right now in this small thing, it is not shown. Only the initial portion has been shown, and you can see clearly that susceptibility, the slope is different. You can also find that susceptibility is not constant. स्लोप का हर जगह पे अलग अलग वैल्यू आएगी इन along this curve. So at this point chi is 0, at this point chi is high values, and so something like, so this is, so chi का value जो होगा, susceptibility will be having different values at different points of the curve. Antiferromagnetism is shown by chromium metal and oxides, MnO, cobalt oxide, nickel oxide, MnC, like that. So these are, so in this case what happens is that you have the spins, there are individual spins at different atomic sites in a crystal. So, but they are aligned opposite to each other, anti-parallel to each other. So when you apply magnetic field, you get a very small positive value of the susceptibility M versus H curve. So this anti-parallel arrangement is the typically antiferromagnetic substance is shown, and the ferrimagnetism is something like in magnetite, magnemite. So in mixed oxides and other ferrites, it is shown, it is found. So the behavior of ferrimagnetism, look at the curve. It is similar to what we observe for the curves are nearly similar to what you saw here in case of ferromagnetism. It will, but the susceptibility is it has mixed oxides and anti-parallel. So it also has anti-parallel arrangement, but the arrangement is such that the net magnetic moment is not cancelled out. There are less number of, so you can see overall it is still, so if you look at the upspin here, there are greater number of upspin than the downspins, and so there will be net magnetic moment. But in case of antiferromagnetic, you were having the thing that actually cancels out the whole. So that kind of antiferromagnetism, the spins are arranged in such a way that they are cancelling out when there is no field present. Ferrimagnetic, it is still a net magnetization remains, and such substances also, when you remove the magnetic field in ferromagnetic substance, there will be some net magnetization over there. So we'll discuss more on this in the next class. So we'll talk about ferromagnetic in greater detail. Okay, thank you.